audio.
So thank you very much to SECPHO for the opportunity and for everyone to listening to us in this workshop on artificial intelligence and photonics. We are more from the photonic side. Artificial intelligence is being very well described by the two talks that we had before, but in general, I believe we all would agree with all people here that in order to have very good artificial intelligence performance, you need as good sensors as you can have. So we are more on the sensor side. So we are working on different types of sensors in order to perform high performance data fusion for combining bidimensional and three-dimensional imaging. And then we have applied it in different applications for advanced robotics, and that's what I would like to show to you in the coming minutes. Essentially, the origin of the company where we have a very original approach and a very good quality results is in LIDAR. LIDAR is a type of sensor which is in all autonomous vehicles, or expected to be in almost all or in all autonomous vehicles, which essentially shines a laser pulse towards the target and then scans the surface. There are different technologies, but essentially you got an image with the echoes, time echoes of the target, and then you are able to reconstruct the image. This is the image. You will see this image some more times because it's what we see from the lab. And if you are very fast and you are very good, you can even do video with these systems. As far as we don't have many time, I just leave you the link to check which type of videos. We have several videos of different types in Beamagine.com applications. You can check it out now or later, and then see how good quality we can get with LIDAR videos with our technology. But out of this technology, what has been working out, and we are relating that to artificial intelligence, is the fact that we've been working with different applications in different industries. The first one obviously was automotive, because of course the rush for the autonomous vehicle is there, and it's a huge market. And we've been working with different partners in automotive, like Automotive, who had the license for the patents. Afterwards, now it's Pioneer, and with Daimler and with Volkswagen and with Santi. And essentially, the large value that we are adding them is the capability to have extremely good data collection units by fusing this 2D and 3D information just from the sensors. So annotation and edition and managing the images is not needed for them. They just take the data and will deliver it, and that's all. Another very interesting activity we're involved in is and related also to robotics somehow, very much, is a project we developed with Thales Alenia Space on ground. We are still not in space, although we are trying to get there with a proposal phase 2 ESA we are now, where we essentially were working in orbital robotics for satellite docking and the pose estimation of satellites. The effect of pose estimation is the 3D information, and that's equivalent for industry-related robotics. And docking, picking and placing things is something that is also very much related to industrial robotics. We developed a system tailored for that application for Thales Alenia, which had extremely large spatial resolution. It was something like 0.05 degrees at the place of being slow, but not having very large frame rate. Because, well, we know a little bit now about LiDARs, and we are able to tailor the specs and know where the limits are, so we can deliver units which are tailored to the needs of the user. Our main goal now. Well, of course, anything related to planetary exploration, rovers, terrain mapping, that's something which can be done with LiDAR. And lately, we are working with Korean companies related to security applications by adding, again, imaging modes in 2D with imaging modes in 3D. We will be in a number of fairs. We are working with applications with scheduled demos at SECPHO, at Samsung, in the coming months, if they allow us to go to Korea, which is not obvious in the current moment, of course. What is the goal? What is the nice thing? Why it works? Why it's so nice what we have? It's so nice because the technology we have developed enables us to have a LiDAR which is different from the other ones in the sense that it's completely solid state. People sometimes discuss if a MEMS is solid state. A MEMS scanner, for us, we understand and Automotive understand it's a solid state because it's comparing that with rotating velodynes and this kind of mechanically moving elements, which is not as optimal as this, which has no moving parts but a MEMS mirror, which is a millimeter mirror, which has absolutely different resonant frequencies of the vehicles. So we can combine that. So we are solid state, and we are also very, very high resolution. We are going to 0.05 degree resolution in some cases, as I commented before. And that's important because in LiDAR, people is very much concerned about range, and people speak of range continuously. But range and resolution are terribly connected because if you had a lot of range, you don't have resolution, you are not able to train the networks, and you are not able to classify anything. So the combination of 2D and 3D plus a high spatial resolution was giving us this high performance. Just as an example, this is what you would see with a velodyne at 120 meters, which is they have a resolution of 0.4 degrees. Is that they have 0.9 meters. So if you want to classify a car at a distance and slam the brakes, you do have a problem because you have to train very, very well your network to say it's possible. But at the same time, if you want to go to the case when you want to classify road debris, is the use case that Automotive guys are looking for. They want to see something 10 millimeters height at 150 meters, which means that you will need a resolution of 0.04, which is 10 times less than current velodyne reference. So if you assume 128 vertical points with that resolution, you are only going to have a vertical field of view of 5 degrees, which is nothing. Because when you go to IKEA, you lose you lose the field of view and you are just pointing at the sky. But if you move in hilly streets, you also have a problem. So our combination of spatial resolution and range is pretty good. We are able to get currently 100 meters of range with 0.05 degree resolution by playing with different trade-offs, which makes a difference. Plus, we've been able to work, we are having this level of resolution enabling us to get to these point clouds we are seeing at 50 and at 100 meters of the person you may see in the right figure, in the left figure, sorry. So we are able to train networks quite well because we have a lot of points for training them, and we are able to customize the unit. There are some videos that you can see there in the slide. Finally, data fusion. The nice thing is that when you combine, the nice thing for us is that original data, when you get a velodyne and an image, normally needs a lot of transformations, which are not obvious, which depend on parallax, which depend on the geometry of the sensor, which depends on a number of things, so they need a correction. And we currently are able to provide seamlessly without any operation because we are able to match by hardware the 3D data we obtain with all types of cameras that you have. We have applications in RGB, we have applications in near cameras, near infrared, short-wave infrared, polarimetric cameras, which are a very funny tool that has now appeared. You see at the right bottom, a polarimetric camera fused with our system, with our 3D system. We can do it with hyperspectral, and we have done it with thermal cameras, so this enables a lot of potential uses. I think I'm running out of time, so I will go a little bit fast and leave you my contact afterwards if you want. This is fusion of 3D LiDAR and RGB. You can do it at different levels. Of course, you keep the full 3D information of the point cloud with the color information or the polarimetric information aside, which is pretty powerful. This is, for instance, the fusion of 3D and polarimetric degree of linear polarization or angle of polarization, which is also, well, it delivers information in particular applications. It's very powerful. This is the fusion of LiDAR and thermal, which is also pretty powerful, as you see. And up to 15 imaging modes, we can provide them with the box you see before. And fuse them in by fusing, diffusing, natural to the active passive imaging mode. You can have up to 15 in a box, which is this one, which looks like a microwave, but that's something going to change in a few months, and where we can embed a CCTV camera, a thermal camera, polarimetric camera, and only in 20 by 20 by 10 centimeters. Of course, we can tailor the things different levels, and we can add artificial intelligence for perception. We can detect pedestrians. We embed data fusion. I mean, there are different options available for anyone interested. These are the typical specifications we have in a LiDAR unit. Also, again, we can tailor that to the interest of any application.
Santi, you've got one or 2 minutes more.
That's all. It's my last slide. Afterwards, I just want to list a little bit the use cases that we found in Industry 4.0, data collection units for training, high-resolution robotic manipulation, pick and place, eyes, for instance, artificial and volume measurement in less loads, container inspection, docking, and post-estimation would be the typical. So with this, I would finish. Thanking all of you for your attention. If you are going to trade fairs like SECPHO or ISEC, we will be glad to see you there. And anytime here in Catalonia is Sant Jordi, so please have a rose and receive my congratulations, my greetings for Sant Jordi. Thank you.
Thank you very much, Santi, for your talk. You can leave your questions here again to all the attendees. I have one question. Maybe it's a bit simple, but when you, let's say, when you have a problem like this one you want to tackle, you want to fuse data from a 3D LiDAR and a 2D camera, right? So one of the problems you start with at the beginning is the lack of data. I don't think it's that easy to find, I don't know, a library that is meaningful for your application with this data. So what do you do in this case? You just go to the field and grab the data yourself?
Yeah, typically we do that kind of things. We got datasets for training our systems. And the other, we are collecting datasets. The plan, in fact, is making them available as soon as we have a little bit more ordered. Then that's something we're working in. But in practice, of course, you can still work with the datasets that are available for 2D data. And out of that, afterwards, make the extrapolation to 3D. So you can manage that way. There are other ways to do that, but that's one of the ways we are doing. In the future, we plan to work in 3D direct image training.
I see. It's a problem, honestly. We have one more question here from Alex Suarez. So what's the advantage of LiDAR imaging over other image processes, and what's the acquisition rate for LiDAR?
Acquisition rate depends on the resolution you want, but the videos that we have in the web are 10 frames per second. So it's for automotive, so you need a frame rate which is agile. If you want a lot of resolution, you can go down to 1 to 2 frames per second. If you want less, you can raise that to 20 or even more higher frames per second.
Okay, and about the advantage of LiDAR over ultraviolet or holographic imaging in terms of information?
The 3D information. You got the 3D data, the whole point cloud. Maybe in holography you can have that, but I've not seen point clouds from holographic data. Maybe there are, but I've not seen them. You can have the discrete points, and you can have the 3D information and the intensity and reflectance information of the object. So 3D would be the main point, I would say.
I agree with you. Okay, so thank you very much.